oceans cover about 3/4 of the Earth. From the surface, they may appear dark, featureless, and empty. But break the surface, and life is all around. The ocean is not our element, but it provides homes for more varied life forms than the land. Until this century, we knew of the sea only what we could bring up in nets. Delicate creatures like jellies, once known as jellyfishes, are nothing like fish. Made almost entirely of water, these creatures would never survive a trip in a net. Filter feeding, a way of eating common to marine animals from corals to some whales, doesn't exist on land. But how do we explore this world, so foreign to our own? 100 feet underwater, the pressure is 4 times greater than at the surface. Farther down, light fades and temperatures drop. The pressure and the cold are more than people can withstand. Even plant life gives way to sponges. Our first attempts to explore the world below the light were crude and dangerous. In 1934, zoologist William Beebe and engineer Otis Barton dangled from steel cable 3,028 feet below the surface in this tub called a bathysphere. On a subsequent trip, the bathysphere was sent down empty. A window leaked. At the surface, the explorers were given a demonstration of water pressure at work. Today, more sophisticated submersibles, like the Nautil, can take explorers 2.5 miles down. From the windows of these deep-diving machines, scientists see into a world lit up by bioluminescent creatures, glowing with chemically produced lights. But less than a dozen submarines have made it to these depths and returned. What other secrets are kept in the dark? There are worlds deeper still. The bottom of deep-sea trenches lie under as many as 7 miles of ocean. We know less about the ocean floor than the surface of the moon. 97% of the ocean floor remains unexplored. Computers draw tantalizing and accurate maps of places like Perth Canyon, below the Indian Ocean. But we can't get there yet. It's a world apart. What spectacular life forms await our discovery? Under the surface of the water in Truk Lagoon lives the largest coral reef in Micronesia. Like all coral reefs, this one began with single polyps, small coral animals best seen at night when they stretch out their tentacles to feed on floating plankton. Polyps attach themselves to hard surfaces and excrete a cup-like skeleton for a home. In Truk Lagoon, the wrecks of Japanese ships sunk in a battle during World War II, laid the foundation for one of the most diverse ecosystems on Earth. This blue chromis fish lives in a gun barrel. Over the last half-century, thousands of coral skeletons became the hills and valleys of a reef. Other animals move into the reef seeking food and shelter. Coral reefs house over 25% of all marine life. Commercial fish, like this grouper, live in reefs, and some sharks rely on the reefs for food. Coral reefs help protect other habitats too. Truck Lagoon's reef serves as a buffer for coastal mangrove forests. Sand roughed away from the reef makes soil for the roots of the mangrove trees. In return, mangroves filter sediment from the land and make great foraging habitat for reef creatures. Mud skippers are fish that live in and out of the water. Reinforced forefins make workable arms, and mud skippers elbow their way between watering holes exposed at low tides. Bulging gill pouches allow them to breathe out of water. Fiddler crabs dine in the mangroves too, before scurrying back to the shelter of the reef. Like all the Earth's ecosystems, coral reefs have suffered from human activities. Dredging and filling for land development, like runways, have hurt some reefs. Other corals die when ocean temperatures rise from global warming. Bleached skeletons are all that remain. Although coral reefs cover a tiny fraction of the ocean, they are the rainforests of the sea. Diverse, fragile, vital.
My definition of a wave, it's a moving palette of ocean energy that invites us as humans to ride along and participate in that movement, that flow of energy.
Scientists wouldn't disagree entirely. Waves are vertical expressions of energy. Waves begin far out at sea, where they're whipped up by the wind. These swells carry energy from the wind across the surface water all the way to the beach. Surfers can ride waves because as the waves roll ashore, they climb. In shallow water, wavelength decreases. The bottom of the wave drags on the sea floor, and the crest of the wave rises, moving along until it breaks. Changes in ocean levels are caused by tides. Tides rise and fall with the gravitational tug of the moon and the sun. The effects of the moon's gravity is the stronger of the two. The effect changes as the moon rotates around the Earth. Physicist James Trefil explains.
When you have the situation of the moon pulling on this side and then pulling the Earth away from the ocean on the other side, it looks like you've got a bulge where the ocean is sort of football-shaped and the Earth is baseball-shaped inside. And then that moves around the Earth and follows the moon.
Twice a day, tides rise and fall, and waves constantly lap our shores. Over time, waves can change the shape of our coastlines and create new beaches. And maybe the surfers have it right after all.
Riding a wave it's dancing with the ocean's pulse, with its mystery. It's like playing music with the ocean.
"99% of all the living space on Earth is in the oceans. For those of us living on the remaining 1%, it would seem that oceans offer an infinite resource. But we're learning their limits. More than 100 years ago, we harvested whales for their oil, meat, and bones. We took nearly 3/4 of all the world's whales before we stopped. Today, most whale species are protected, but a steadily growing appetite for fish has threatened a host of other marine animals. Sharks, heirs to a 400-million-year-old history, are at their lowest numbers ever. Some salmon species have been listed as endangered. And harvesting one species often results in catching other animals. The term for animals caught accidentally is bycatch. We haul in 20 million tons of bycatch each year, including protected marine mammals. The Japanese fish market opens at 4 a.m. By 8 a.m., over 20,000 fish, like these tuna, have been sold. Worldwide, we now harvest some 95 million tons of fish a year, an amount the oceans cannot sustain. 70% of the major fish species, like tuna, swordfish, and marlin, are overexploited. While we're over-harvesting well-known fish stocks, we're discovering a multitude of new species in the deep. And as we explore, we're finding more than food. Because many marine species cope with their world chemically, marine biochemical diversity offers a new resource for medicines. Recently, scientists discovered the chemical discodermalide in deep-sea sponges. Sponges may produce this chemical in their ocean environments for their own protection. Scientists, like Dr. Shirley Pomponi, hope to use the chemicals in the treatment of cancer. These are multiplying cancer cells. Treated with doses of discodermalide, the cell structure breaks down and the multiplying stops.
When something that we collected from the deep sea using our submersible yielded a compound that we discovered that now will be able to be used to treat cancer. So that's pretty exciting.
Even more exciting is that discodermalide can be produced through chemical synthesis in the lab. removing the need to harvest more sponges. Our ability to search the depths for foods and medicines must be matched by our willingness to manage the resource, or we'll lose it. The oceans cover 3/4 of the Earth. Mix all this water with wind, add gravity from the moon, and spin it with the rotation of the Earth, and you've made a global machine that moves energy around the world.
If you look at the Earth sort of large scale, the main thing that's going on the surface is that the heat is coming in. There's more heat at the equator than at the poles. And so the function of the atmosphere in the oceans is to move that heat northward, to kind of even things out. Otherwise, you'd have the ocean boiling at the equator and freezing at the pole.
Currents not only help control temperatures on Earth, they circulate nutrients as well. Studying how currents move heat, nutrients, and even plastic ducts is serious work for oceanographers Jim Ingram and Curtis Ebsmeyer. These scientists map surface currents by plotting the path of a lost cargo of rubber ducks. Studying the way the tub toys move and float in a pool helps the oceanographers understand how the ducks made it from the mid-Pacific to the shores of Alaska. The information collected in the pool is loaded into a computer model that takes into account wind speed, drift, and waves to simulate the duck's accidental trip. As each duck arrives on the virtual shore, more information about surface currents takes shape. We know now that surface currents are streams of water as much as 50 miles wide, affecting the movement of objects to depths of 100 feet. Such information serves us well. When oil spills like the Exxon Valdez happen, knowing where the oil is likely to move may save shorelines and sea life. There are currents at all levels of the ocean. Deep currents move mysteriously along the sea floor. Mid-depth currents travel in complex patterns about 3,000 feet down. Over 90% of the bottom of the ocean remains unexplored. We do know that currents move the ocean floor itself, continually reshaping the part of the Earth's surface we're just beginning to understand.